everyone, and welcome back. Today we're going to be continuing our exploration of single variable calculus and be focusing on two classes of applications that you can solve with single variable differentiation methods, in particular optimization and related rates. Although the problems that we will be solving today probably aren't going to be problems that you will solve in your own personal life, the mechanisms and ideas that we use in solving these problems can usually be used in most single variable scenarios. So let's first off go over some of the basics of single variable differentiation that you definitely should understand when trying to do optimization and related rates problems. To sort of guide our intuition, let's just consider a very basic function that most of us already know, and that's the general quadratic function in one variable, ax squared plus bx plus c, with the condition that a, that leading coefficient, is not equal to 0. So just based on mathematical foundations principles, if you have a leading coefficient that is positive or negative, you can in some sense guess the overall behavior of your function. So if the leading coefficient is positive, then what we're going to have is a parabola that's sort of facing upwards, and if the leading coefficient is negative, then you're going to be having a parabola that's sort of facing downwards, right? Assuming that the horizontal axis is x and the vertical axis is y. So in either of these cases, what we have here is a vertex in both of these cases, but these vertices are different classifications. For the first case, what we have is a local and also a global minimum value. And in the a less than 0 case, what we have is a local and also a global maximum. So what's so true about derivatives at this particular point? So at local minimums, what we have here is that the derivative at this particular point is equal to 0, and that's actually true for both the local min and the local max case. The only difference is that the second derivative at this particular point is going to be positive versus the second derivative at that local min is going to be negative. And in some sense, what we're hinting at there is that the function is concave up around that particular minimum value, and the function is concave down around that local maximum. So if we're like, okay, well, where exactly is this particular vertex located? We can find that algebraically because we can just set the derivative of this function, which we know by the power rule just is going to be 2ax plus b, set that equal to 0, and then solve that resulting equation for x. So what we're going to have here is that the x-coordinate for the vertex is just going to be equal to minus b all divided by 2a, and that's going to give us our particular result. So, if we differentiate a function blindly without any graphical intuition, set it equal to 0 and solve for x, then all we can really say is it is a local extreme point, right? So it's either a max, a min, or neither of those, right? So even if it's not a local max or min, some people still call it an extreme point. So we're like, okay, well, this is the extreme point, so how do we know if it's a local min or a local max? So we can take that first derivative and differentiate it again. We're going to be like, okay, the second derivative is just the derivative of that linear function, which in this case is going to be equal to 2a. And in this particular case, if a is greater than 0, that means f is always, or in particular at this particular point, concave up. And if the function is concave up at a local extreme point, that means f, in particular the vertex of this f, is a local minimum, which agrees with our intuition from our graphical perspective. And if a is a negative number at this particular point, in this particular case it's a constant function, so it's going to be true for always, always for this function on its entire domain. So f will always be what we call a concave down, right? And if it's concave down at a particular point, that means if it has a vertex, that means the vertex is a local max. Right, so those are some of the basic principles that you definitely need to understand when we jump into optimization and related rate problems. Now that we've reviewed the basics, let's get into our first example. So let's suppose that we have a farmer and they want to fence a rectangular field that is adjacent to some river, and let's assume that we do not need any fencing along that river. In particular, maybe the animals cannot swim, so you don't have to worry about them swimming away. And let's assume that they want the area to be 180,000 square meters so that the cattle can roam happily ever after. What are the dimensions of the fence that are needed in order to require the least amount of fencing, possibly for cost purposes? So, every time you have a geometric problem, sometimes it might be easier to start off by drawing a picture. So, in this particular scenario, what we have here is we have some field, and it's going to have some fencing around it. And let's assume that this field is adjacent to a river, right? So this is our river, and this is our field. So we want this particular area for this field, A, to be equal to 180,000 square meters, but we don't know the dimensions of this particular field. And since it's rectangular, we can assume that these corners are 90 degrees, right? So let's give these sides some names. So let's call this X, X, and Y. So we need to figure out what these dimensions X and Y are in order for this area to be 180,000 square meters, such that the sum of X, X, and Y is as small as can be. So let's list these criteria out in equation format. So we know that the perimeter must be equal to X plus X plus Y, X plus X plus Y, which is just a fancy way of saying 2X plus Y. And we know that our area is equal to X times Y, and we want this to be equal to 180,000 square meters. So these two things are given to us. So what exactly do we want? So we want the least amount of fencing. So we want the least amount of fencing, which means we want to minimize P with respect to X and Y. So if we know that X times Y is equal to 180,000, we can solve this equation for one of these variables because our P function has two variables and we only know single variable calculus, right? So we can't differentiate this with respect to X and optimize, at least not in an efficient way. So we're like, okay, from this equation I can solve, for example, Y, and we can say Y is equal to 180,000 all divided by X, and then we can substitute that into the first equation. So once we have that, that means our perimeter function is now a function of X only, and that's going to be equal to 2X plus Y, and Y is given to be 180,000 divided by X. Right? So once we have this particular function, now all we need to do is differentiate that and set it equal to 0, solve for x, and then just make sure that it is a thing that minimizes that particular parameter, and then find the x and y that makes the original problem true. So p of x is equal to a function of x, so we should be able to differentiate that. So taking the derivative with respect to x, the derivative of 2x is just going to be equal to 2. The derivative of 1 over x is the same as the derivative of x to the minus 1. Minus 1 will come down and change that to a minus 2. So we're going to have 2 minus 180,000 all divided by x squared as the derivative of p. And now all we're going to do is just set this equal to 0 and solve this equation for x. And that should give us x values that minimize our perimeter. So what we can do is we can multiply both sides by x squared. That's going to give us 2x squared minus 180,000 is going to be equal to 0. We can add 180,000 to both sides and then divide both sides by 2. And that's going to give us x squared is equal to 90,000 square meters. And then that means that x is just going to be equal to the positive square root of that, which is just going to be 300 meters. Right? So this value of x is going to allow us to have a minimal perimeter. So that means our associated y value will be equal to 180,000 divided by our x value, which is found to be equal to 300, which is the same as, so we can cancel out two zeros from top and bottom, so that's 1,800 divided by 3, which we know to be equal to 600 meters. Right? So those are the dimensions of the fence that will minimize the perimeter. Right? So that's pretty nice, pretty easy. Let's look at another example. So let's consider this. Suppose you have a 3-inch by 5-inch note card, and you're to cut out square cutouts from each of its corners in order to fold it into an open top box. What is the area for each of those little square cutouts that will maximize the volume of the box that you're trying to build? So again, we have a geometric style problem, so drawing a picture always is a good place to start. So let's draw our 3-inch by 5-inch note card. So let's assume that this dimension here is 3 inches. And let's assume that this distance here is 5 inches. So what we're going to do is we're going to be cutting out these little squares out of each of the corners. And we don't necessarily know how big they need to be, so we need to give them a name. So let's call each of these sides x, each of these sides x, and each of these sides x. Right? And what we're going for is, what is the area for each of these square cutouts? Right? So these areas are going to be equal to x squared. So that's the goal that we're going to be aiming for throughout this entire problem. So once we have this particular cutout done, then what we're going to be doing is we're going to be taking these little sides and folding them up, and then we're going to be making a little box. All right, so let's see if I can draw a nice little box here. All right, so here's our box. Cool. So if this distance right here is 5 inches, notice that we're taking 2 x's away from this. So that means this distance right here will be 5 minus 2x inches. And notice that this distance right here, this used to be 3, but we're taking, again, 2 x's from it. So that means this distance here is going to be 3 minus 2x inches. And the height of this box is going to be x inches, right? So obviously we need to figure out what x is, and obviously we want this volume to be as large as possible. So that's pretty much the outline of what we're going to do. Now it's very important to understand that these dimensions cannot be negative. So 5 minus 2x must be greater than 0, 3 minus 2x must be greater than 0, and x must be greater than 0. Obviously, if x is equal to 0, then you don't have a box. Therefore, we mandate the following restrictions to our problem. So our engineering restrictions are as follows. So first, x must be at least greater than or equal to 0. 2, 2x must be less than or equal to 3, right? Because 3 minus 2x must be greater than or equal to 0. And also 2x must be less than or equal to 5, right? Because 5 minus 2x must be greater than or equal to 0. So if we combine all three of these together and look at their overlap, that means x must be a number in between 0 and 3/2. Right, so that's the domain for our particular problem. So now that we know the length, width, and height for our box, let's try and create a volume formula for our box. So since we only have one variable x, we're definitely in the right direction. So we have length, width, and height. So that's the equation of our box. And we can expand that, right? So 5 minus 2x, 3 minus 2x times x, combine like terms. So we're going to have that our volume formula is going to be equal to 4x cubed minus 16x squared plus 15x. And once we have our volume formula, then we can differentiate and set equal to 0. So since we just have a polynomial, its derivative is actually quite easy. So the derivative of 4x cubed is just going to be equal to 12x squared. The derivative of 16x squared is going to be 32x. And the derivative of 15x is just going to be equal to 15. We're going to be setting that equal to 0, solving for x, and hopefully it gives us something nice to work with. So it's definitely a quadratic equation, so definitely trying to factor it is a good place to start, but one can verify that this is not factorable over the set of integers or rational numbers. So, using the quadratic formula, we're going to have x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So we can expand 32 squared minus 4 times 12 times 15, and you're going to have that that's going to be equal to 304, and that's all over 24. You can take out a 4 out of 304, and you're going to be left with, you can take 16 out of 304 actually, whose square root is equal to 4, and that's going to come out to 32 plus or minus 4 square root of 19, all divided by 24. And we know that 4 divides evenly into 32, 4, and 24, so we can definitely simplify this. So we're going to have x is equal to 8 plus or minus the square root of 19 all over 6. So we have two values of x that is going to give this to us, but which of these values of x is actually going to give us what we want? So if we look at our function for v, which is a cubic polynomial, and in particular x equals 0 is one of its x-intercepts, what we're going to have is this particular type of shape. And here, this is going to be our 3/2 point, and then we're going to have a point over here that doesn't really matter, but that's going to be equal to 5/2 if you really want to know what it is, right? But keep in mind, x must belong to the interval 0 to 3/2. Therefore, this little region here is the only region that makes sense to us, right? So this point here is the solution to our problem in terms of the dimensions of each of those little square cutouts. And this also is a point for which the derivative is equal to 0, but that point is not what we want. So what is the value of this point and what is the value of that point? So notice we have 8 plus or minus. The plus is going to be the bigger number in that case. So that means this particular number here, that's the 8 plus the square root of 19 over 6. And that means this value right here is the 8 minus the square root of 19 over 6 value, right? So the x value that generates a maximum for volume, I'm just going to call it x max, is going to be equal to 8 minus the square root of 19 divided by 6. Right, and we can name the other one just so that it doesn't feel left out. So x min is going to be equal to 8 minus the square root of 19 over 6, but we're assuming that we can't have negative volume, so this solution doesn't really have much purpose for us in this scenario. Right, so once we have our maximum value, and you can find a decimal value for that, you can say that x max will be approximately equal to 0.6069 inches to 4 decimal places. And then from here we can find our area for each of those cutouts. So that means the area for each cutout will be equal to 8 minus the square root of 19 all divided by 6, the quantity squared. And you can find this in approximate value to be 0.3683 squared inches, right? So that's the area for each of those little square cutouts in order to make your box have maximum volume, right? So not too bad. Just of course we use the quadratic formula, so definitely keep that in the back of your mind just in case you need it later. The next problem that we're going to look at also is a geometry-based problem, but we're not going to be looking to minimize or maximize anything. So let's give it a read through. Suppose we have a spherical balloon that's containing helium gas, and it's being filled up at a rate of 3 cubic centimeters per minute. How fast is the surface area of the balloon changing when the diameter is 16 centimeters? So a couple things to mention here. It's being filled up at a rate of 3 cubic centimeters per minute. So don't necessarily have to know how big the balloon is at the start of observations here. In some sense, we can assume that it pretty much has a radius of 0 and is going to infinity, assuming that it has the potential to do so, right? And obviously, we want to figure out how fast the surface area of the balloon is changing when the diameter is equal to 16 centimeters. So since the diameter is also going from 0 to infinity, it's obviously going to pass through 16 centimeters at some time throughout its lifespan, right? So we should be able to see, how fast is the surface area of the balloon changing, where we only know how fast the actual volume of the balloon is changing. So we have two different rates going on here. The surface area is changing and the volume is changing. So things that have these types of rates and they're sort of, using one rate to find another, these are called related rates problems. So as usual for geometric problems, drawing a picture sometimes will help you figure things out. So what I'm going to do is I'm going to attempt to draw a sphere here. So here's our balloon at some point in time, and obviously it's going to have a radius at some point in time, and that radius is obviously not going to stay constant. So we should know that the volume of a sphere with a fixed radius is equal to 4/3 pi r cubed, and the surface area of a sphere, in case you don't already know, is actually equal to the derivative of the volume of the sphere with respect to its radius. And if you know that particular thing and you haven't memorized the surface area formula, you can just find that it's equal to 4 pi r squared. So that's pretty neat. So we have the volume, which we know is changing, and the surface area, which is also changing. So how fast is the surface area changing when the diameter is 16 centimeters, provided that the volume is changing at a rate of positive 3 cubic centimeters per minute? So hopefully we have all the equations we need, but if we need more equations, we'll introduce them as is. So what do we have? So when the diameter is equal to 16 centimeters, that means the radius is equal to half of that particular amount, which we know is going to be equal to 8 centimeters. All of our equations have r in them, so in some sense there's no need to introduce diameter here. So, if we know that the volume is given by this equation, we can take the derivative of both sides of that relation with respect to time. So dv dt will be equal to the derivative with respect to time of 4/3 pi r cubed. Keep in mind, radius does change with time, so radius is not a constant here. So this is going to be equal to 4 pi r squared times dr dt from the chain rule. Right? So this is an expression for dv dt, and it's already given that this is equal to 3 cubic centimeters per minute. So we have this particular relation. We don't know dr dt, we do not know r squared at any point in time, but it does gives us something that we can work with. So again, let's just recap what we're looking for. So we want how fast is the surface area changing when the radius is equal to 8. So that's what we want. So obviously we should take the derivative of our surface area relation with respect to time, and that's going to be the derivative with respect to time of 4 pi r squared, which we know is going to be equal to 8 pi r times dr dt. Right? So what is dr dt? Well, from this particular relation, we can actually solve for dr dt, because dr dt will be equal to 3 over 4 pi r squared. And then we can just substitute that into this equation, and that will get rid of that dr dt thing that we don't know. So our surface area is changing with respect to time at a rate of 8 pi r times 3 divided by 4 pi r squared. And then we can clean this up a bit because definitely some things do cancel. So we have a pi that cancels, we have an r that cancels, we have an 8 that cancels with the 4 and makes that a 2, and 2 times 3 is just going to be equal to 6. So we're just going to be left with 6 divided by r, and that's how fast our surface area is changing with respect to time with respect to radius. So therefore what? So we want to just know what is ds dt when r is equal to 8. So that means ds dt when r is equal to 8 is just going to be equal to 6 divided by 8, which is the same as 3 divided by 4, or as a decimal, 0.75, let's see, this is surface area, so that's going to be a squared unit since it's a two-dimensional quantity. 0.75 squared centimeters per minute will be our answer for that problem. Right, so definitely always start off with your geometry problems, differentiate with respect to time since we're looking for rates, and see if you can algebraically manipulate things in order to get what you want with what you have. The next problem that we're going to look at is also a related rates problem. Let's assume that you have a fixed length ladder that is 15 feet long and it's leaning against a building. And due to instability, when you step on it, the base of the ladder begins sliding away from the base of the building, which means that the top of the ladder is also sliding down the building also. Let's assume that the base of the ladder is sliding away from the base of the building at a constant rate of 0.5 feet per second. So, when the base of the ladder is 5 feet from the base, how fast is the top of the ladder sliding down the building? So, again, we have a geometry-related rates problem, so drawing a picture may be handy in this particular scenario. So, if we draw a little triangle to sort of simulate what we're looking at here, let's introduce a couple colors here. So let's assume that this is a right triangle for simplicity purposes. Obviously, this distance here is going to change with respect to time. This distance here also is going to change with respect to time, but this distance is assumed to be a fixed length at a length of 15. And if this is a point in the present, at some point in the future, this is the scenario that you will have. So you'll also have a right triangle with this being 15 and the length and height being a different value of y and x with respect to time. So if we differentiate this particular triangle with respect to time, then since we're assuming it's a right triangle, what we have here is that x squared plus y squared will be equal to L squared, where x and y change with time and L does not change with time. So in this particular case, we're going to have 2x times dx dt plus 2y times dy dt is equal to 2L times dL dt, but we're assuming that L does not change with respect to time, therefore this is assumed to be equal to 0, which means the entire right-hand side is going to be equal to 0. Notice that we have a 2 in each of these terms, so we can divide all sides by 2, and we're going to have a more simpler relation to deal with, in particular x times dx dt plus y times dy dt, and all of that's going to be equal to 0. So this is the first equation that we can work with. So what are we aiming for? We want to figure out how fast the top of the ladder is sliding down the building. So that's how y is changing with respect to time. So let's go ahead and solve this equation for dy over dt. So once we do that, we're going to have dy over dt is going to be equal to minus x divided by y times dx dt, if manipulated correctly. So this is our particular equation. And we know how fast the base of the ladder is sliding away from the base of the building. That was given to be dx dt is going to be equal to a fixed rate of 0.5 feet per second. Right? So that was given to us. So when x is equal to 5, because we know x, that's what we're interested in, we know dx dt, what is y in that particular picture? So let's sort of draw out our little picture here again. So this is going to be a fixed length of 15. This is a particular point in time for which this distance is 5. So we want to figure out what that y value is at that particular time. So since, again, this is a right triangle, that means that y will be equal to the square root of 15 squared minus 5 squared. And once we simplify that, that's going to be equal to the square root of 200, which we know to simplify to 10 square roots of 2. Right, so when x is equal to 5, y is equal to 10 square roots of 2, dx dt is equal to 0.5 feet per second. So we can find how fast the height of the height of that ladder is sliding down that building at this particular time. So that means dy dt, so dy dt, when x is equal to 5, will be equal to what? So that means this is going to be equal to minus 5 over y, which is 10 square roots of 2, times dx dt, which is given to be 1/2 feet per second. And you can find as a decimal, that's going to be approximately equal to negative 0.1768 feet per second. And keep in mind, if you forget the minus sign, that's a really, really big error, because since our dy dt is negative, that means it's sliding down the building, not sliding up, right? So that problem isn't too bad. It just required a little bit of right triangle thing and Pythagorean theorem. So let's take a look at another example that is also a little bit fun to work with. For our last example, let's suppose we have a right circular cone that has a height of 30 centimeters with a 20 centimeter base diameter, and let's assume that it's initially filled completely with water. But water begins to leak from the bottom little point at a rate of 2 cubic centimeters per second. When the volume is a quarter of its full amount, how fast is the depth of the water changing? So again, we have a geometric problem. We know how some things are changing, and we want to know how something else is changing, so this is definitely a related rates problem. So, a geometry problem, drawing pictures in the start sometimes helps, so let's assume that this is our right circular cone. So, we know that this height right here, this distance here, this is given to be, let's see, a height of 30 centimeters, and the base diameter is assumed to be 20, which means that the base radius is going to be equal to 10 centimeters, right? So obviously it's going to be initially full with water, right? But after some time, t, which is obviously greater than 0, we're going to have a cone that's going to look like this instead, right? So now our water is sort of just down to that point, right? So obviously this is going to be some height h, and also we're going to have some radius r that's also going to be changing with respect to time. So this is our t is equal to 0 picture, and this is our t greater than 0 picture here, right? So a couple things that we should have mentioned from the contextual point of view, that dH dt is going to be negative for all t that is greater than 0 because the height is sort of going down and is eventually going to reach 0. And in particular, when t is equal to 0, the diameter being 20 it implies that our radius was equal to 10 and our height was equal to 30. So what are some geometry formulas that we definitely need to understand here? So obviously the volume is decreasing at a rate of 2 cubic centimeters per second, so that's obviously dV dt, where V stands for volume. So the volume of a right circular cone is going to be 1/3 pi r squared h, right? So how full is the cone at time t is equal to 0? So V full, I'm going to call it, but again, this is just t is equal to 0, is going to be equal to 1/3 pi r, which is going to be equal to 10 squared h, which is equal to 30. So that's going to be equal to 10 squared 100. 100 times 30 is 300. 300 times 3 is going to be, what is that? 100 times 3 is going to be 1,000 divided by 3. There we go. So 1,000 pi cubic centimeters. So that's our initial volume. So whatever it is when it's a quarter is going to be a lot less than that. So let's see what that would be. So a volume when it's a quarter full is going to be a quarter of its full volume, V full. So that's going to be a quarter of 1,000 pi cubic centimeters, which is just going to be equal to 250 pi cubic centimeters. So we know how full our cone is going to be. We just need to figure out how fast the depth of that cone is changing with respect to time. In particular, we want to find dH dt when V is equal to 250 pi cubic centimeters, right? So that's the problem that we're aiming to solve, right? Now, what exactly are we going to do here? So if we find dV dt for this particular expression, notice that we're going to have r squared, which obviously changes with respect to time. We're also going to have h, which is also going to change with respect to time. So if we dV dt that particular expression, we're going to have a product rule, which can be a little bit messy. So let's see if we can eliminate one of those variables into one of the other variables. So for example, solve r with respect to h or h with respect to r, and make volume an equation with only one variable in it. Then it's going to be a little bit more easier to work with. So let's sort of look at a time lapse of our cone from a lateral perspective. So let's assume that this is our cone, and this is our height, and let's assume this is that. And let's also assume that this is the height at the point for which we're interested in, right? So we know that our initial height is going to be 30. This particular height is equal to h. This particular radius here is going to be equal to 10, and this particular distance here is r. So if we look at these particular triangles, they're just similar triangles, right? In particular, where r is going to range from 0 to 10, and h, which is obviously going to range from 0 to 30. So since these are similar triangles, that means their lengths are going to be proportional to each other, right? So that means h divided by r will be equal to 30 divided by 10, which is just the same as 3. So we have h divided by r is equal to 3, so we can solve this equation for h, which is going to be equal to 3r. Keep in mind we're looking for dH dt, so that's why I'm sort of solving for h here instead of r. If you were looking for dr dt, you'd probably solve for r here instead of h. But now we have the puzzle piece that we were looking for this whole entire time. Right? So height is being represented with respect to radius, so all is going to be good. So again, volume is equal to 1/3 pi r squared h, and h is equal to 3r, right? So if you're like, oh, h is equal to 3r, but if I substitute that, that's going to give me an equation with r in it, and I don't know dr dt. So I can again solve that for r instead, and that's going to give us r is equal to h over 3. And then when we substitute that into this equation, that's going to give us pi r squared h, and that gives me an equation with only h in it. So that's actually what I want, right? So you can sort of think about it that way to sort of see which equation you want and how do you want to solve for it. So let's just clean this up just a little bit. That's going to be equal to v is equal to 1/3 pi. That's going to be h cubed all over 3 squared, which is 9, which is just going to be the same as 1 over 27 pi h cubed. Okay, cool. So when our volume is quarter full, that's going to give us 250 pi. What is going to be the height of that particular triangle? So that height is just going to be equal to 127 pi h cubed, and I should be able to solve for h in this particular equation. So you should see that these pi's will eliminate, and then we're just going to have that h is equal to the cube root of 250 times 27, which actually simplifies quite nicely to 15 times the cube root of 2, right? But again, if you don't want that cube root, you can leave it in that form because we're probably going to go for a decimal value anyway. Right? So once we have our v equation and the height for which we need, because we need to plug this into the derivative later on, we just need to figure out how dh dt is changing. So dv dt, since we have a function of h only, that's going to be equal to 1 over 9 times pi h squared times dh dt. How fast is our volume changing with respect to time? Well, we know that that's going to be equal to minus 2 cubic centimeters per minute. And this is going to be equal to 1 over 9 pi h squared. And when h is equal to 15 cube roots of 2, so we're going to have 15 cube roots of 2 squared, and this is going to be dh dt when the volume is quarter full, right? So once we solve this particular equation for dh dt, we can find that dh dt when the volume is a quarter of what it used to be when t was equal to 0 is going to be approximately equal to negative 0.0344. And since this is height, this is just going to be a one-dimensional quantity. So this is centimeters per second, right? And since it's negative, that means it's decreasing, which matches our intuition. So those are some of the common basic problems that people solve with optimization related rates. Even though you might not solve these, the tools and mechanisms that we used here today definitely can be used to solve other single variable optimization and related rates problems. Hope you enjoyed this video, and I'll see you in the next one. Take care.